Machine learning and artificial intelligence has revolutionized the way we approach many problems in finance, particularly lending. So the idea of predicting who is going to be, who should we lend to, and who won't we lend to. So the idea is we're able to feed in a lot of different data, a lot of data that wasn't previously available. We feed it into a large neural network, and we are able to predict better than historically who is a good credit. And this in turn has opened up credit to a lot of people who wouldn't have gotten loans previously. AI and machine learning has also had a huge effect in portfolio construction and asset pricing, among other areas of finance. So what we're going to do in this presentation, in this collab notebook, is we're going to go over using a deep neural network to predict. What we're going to do is we're going to try to predict which banks will make more small business loans, right? So to give you a little bit of an idea, a little bit of background, context, and first I'm going to talk a little bit about this McKinsey document, and then give you a little bit of history of these methods. But one chart, so this is the McKinsey document right here, and I've gone to Exhibit 4, and this is, and definitely if you have the time, read the McKinsey document, but I want to point out this Exhibit 4 here. So you can say whether you think AI will work out or won't work out, but the fact is we have financial services here. What we have on this x-axis is current AI adoption, and on the y-axis, the vertical axis, the future AI demand trajectory. So what we see here is financial services has both a already high current artificial intelligence adoption and is going to increase its artificial intelligence well, fastest, right? So this is even above high tech and telecommunications. So not only is the current adoption high, but the growth rate of AI use is very high in financial services. So these methods are being used and will be continually in demand. And I would argue they are being used because they really have shown results, right? What I'd argue is this is result driven. This isn't just we are able to make better lending decisions. We are able to construct better portfolios and so forth. A little bit of the history before we go into this to kind of explain why this has gotten so popular recently. Neural networks have been around for quite some time, but they have a lot of parameters. So it was difficult to find the solutions to them, particularly as the networks got larger. Within the last 20 years, we've had really great progress in hardware, so particularly with parallel computing and graphics cards. So as graphics cards be able to improved, we were able to build larger and larger neural networks, and then this caused, right, it spurred a lot of research in the actual neural network. So now that we were able to estimate larger networks, a lot of research went into convolutional neural networks and recurrent neural networks and now transformers and so forth. So it really kind of spurred a lot of research on the actual design and mathematics side of it. And now neural networks are widely used. When you chat with your bank, there might be a chatbot talking to you. When you make a letter on your phone, there's a neural network realizing that you're saying A and B, and what we're going to use here is broadly speaking, when you start drawing an A, the neural network, the convolutional neural networks are used a lot for this. However, broadly speaking, basically it takes this 2D image and flattens it out into a vector and then looks for a pattern in the vector. And that's how it tells whether it's an A or not. And so we're going to use those same methods to figure out, okay, which bank is going to lend, right? So we instead of taking a 2D image and flatten it out, we just have a vector of inputs, and then we're going to try to use that to train and then predict which banks will lend. So good, yeah. So I hope you're interested in this area, and I hope this notebook maybe gets you started. So what we're going to do is we're going to use Tensorflow. we're going to use TensorFlow and Keras. There's many frameworks, two big ones right now, TensorFlow and PyTorch. Broadly speaking, TensorFlow is out of Google, PyTorch out of Facebook. So what we're going to do is we're going to load, and Keras makes TensorFlow creating neural networks very easy with very little code. So main things, we're going to use pandas like always, but here's our TensorFlow and our Keras, sorry. And then we're going to use a little bit of scikit-learn for linear regression. So we'll go ahead and load the libraries. And all of this we don't have to install anything. These are already available in our Colab notebook. And what we're going to use here is data. So what we're using are good old pandas to read a CSV file, which is compressed. It's hosted as a gzip file on GitHub. So we can go ahead and kick that off and pull in that data set. And so what this is going to be is a data set this is a panel, which means we have every bank and each bank over time. So we have both cross-sectional and time series. So this is going to be a panel. We can take a quick look at it and see, okay, we have quarter. This is the unique identifier for the bank. We have total assets. And I've already lagged some of these and so forth. So now what we want is so these are the only columns we want. Maybe interpreting a little bit of these. These are my own titles, which may not be obvious, but this is total small business loans, but the percent change. This is the tier 1 leverage ratio lagged. We're going to look, we want to predict, so we're looking at every input variable, which now that we're, if we were talking about a regression, this might be called a right-hand side variable, exogenous variable, or so forth. There's a little bit of new terminology when we go over into neural networks. We generally tend to call these features, and then what we want to predict is the target. So in other words, what we want to predict, the target would be the total small business loans, and then these would be features, tier 1 level, all the things that were lagged 1 year. Total small business loans over total assets, return on assets, non-performing assets, so forth. This is not very important. We're just going to compare a neural network with a regression. So let's go ahead and simply extract the columns that we want. We can take a look at the data here. As you can see, there's a lot of not a number. So for certain banks over certain time periods. So we're gonna go ahead and get rid of those here with our drop NA. And then this was also part of a research on minority-owned depository institutions. So what we wanted to see is could we increase or how sensitive was the lending by these MDIs to their capital levels. So that's where we're going to create a couple indicator variables. These are interaction variables. These are interaction variables between MDI indicators and the leverage ratio. And if you're not familiar with the leverage ratio, this is simply what we're looking at is how much capital the bank, how much capital cushion the bank has. So let's go ahead and do that. And that's fine. And now what you should see is if we actually take a look at the data, we've removed the NAs, and now we have some interaction terms over here. So that's good. The next thing we want to do is we want to orthogonalize. We're going to orthogonalize the tier 1 leverage ratio with respect to total equity. So this is actually stated backwards. Now, this isn't the idea of this notebook, but this is something for you to know. What I'd like to do is include the tier 1 leverage ratio and also total equity. However, these things are highly correlated. So what we're going to do is we're going to run a regression where we have tier 1 leverage ratio as the left-hand side variable, and the right-hand side variable is total equity over total assets. And then we are going to use the residuals in this regression as our tier 1 leverage ratio, which is orthogonalized, meaning when we run this regression, if you kind of remember anything about regression, the residuals are going to be orthogonal to the total equity over total assets. They're going to be uncorrelated, right? So then what we can do is we can include those residuals as the part of the tier 1 leverage ratio not explained by total equity. right? Or total equity over total assets. And again, the correlation between the residuals and total equity is going to be 0. So that's what we're going to do here. This also brings up an interesting point to remember which is again a little odd. This is where you can sort of tell the R language was really created for statistics, and Python, the statistics was kind of bolted on after. But you have to be careful if you use this linear regression. This standard error that it provides is not the standard error of the residuals. I believe it's a standard error of the slope coefficient. So what we have to do then is go ahead and create observe. We have to take our observed values and then calculate predicted values, and then take the difference between the observed and the predicted and calculate that by hand, and this will give us our residuals. So right here, this is where we calculate our residuals. We calculate the predicted value given the slope and intercept, and then calculate the residual values here, and these residual values we are going to use in our neural network in place of the tier 1 leverage ratio. So I already ran that. Good, we can go ahead and do that. Now, one thing that's interesting to neural networks is it's a good idea to normalize the data before you feed it into the neural network. The neural network, the optimization can be sensitive to the data, to how the data is fed into it. So you generally tend to get better results, better predictions if you normalize the data before you feed it in, and then when you make the prediction you unnormalize it, right? So what we're going to do is we're going to normalize the data by subtracting out the mean and dividing by the standard deviation, and then when we make the prediction we are going to sort of unnormalize it. Good. So we'll go ahead and do this, and this is going to normalize every column, every feature, and the target that we have, and then we and I have it again named as input and out here. Remember, this is because I've worked in a lot of this prior to neural networks, but you might want to call this features and target. But so we'll break this into two separate sort of input and output, features and target, and we're also going to take a look at it, visualize it to make sure everything looks good. They're not. So there we go. So this is our scatter plots of our features. Now we're at the point where we can go ahead and construct our neural network. So, and let me say, stepping back for a second, one of the really interesting things about working with neural networks is it's a little different than statistical research. So the idea here is, if in econometrics and in statistics, we often try to figure out, what's the root cause. We're answering kind of these types of questions. We're trying to validate theoretical models and so forth. Whereas, and you can do that with neural networks, but neural networks, I find the real focus is on application. It's on prediction. It's on how well does your model predict. We don't really care how it's making its prediction. We just want to know how well it's making its prediction. So what we're doing here, and what you'll see all the time when anyone's working with a neural network, because we always want to see how well does it test out of sample, right? So we're going to split this into training into test samples. So and we can do this with this Python code here. So the train test split is going to output train test, and we can simply assign it with this notation, train, comma, test, comma, and so forth. So doing this, and our test size is going to be about 33%. So given this, we are going to have, and here the X is our inputs, Y is our output, right? So it's splitting the inputs and it's splitting the output. So we're going to train our network on this, on X train and Y train, and then we're going to test it with X test and Y test and see out of sample how well it predicts. To construct the neural network, that is in this set of lines here, and again, this is uses Keras, which is which is great. So we're going to create a sequential neural network where we're just going to start stacking these things. So we have a dense layer. This is our input dimension. And then we have an activation. We're using a ReLU activation, which works fairly well. I may provide a link, but there are other activations that we can use, and I find this one tends to work very well. Then we have now a dense. We really don't have to worry about what exactly everything means here. However, what a dense neural network means is that every node is connected to every other node, right? So I mean, so that's what we mean here. Good. And then we have a final linear layer. So this is going to be a dense node, but it's going to go into our one prediction, right? It's going to drop down into one. So we have, a layer 100, a layer with 100, and a layer with one node, right? And then this is the activation, and this last one is a linear. So so we're constructing our neural network there, and then here we're going to go ahead and compile it. The loss is our prediction error, right? So this is, we're using mean squared error, which broadly speaking, it penalizes large errors, not really small errors, and so forth. Again, you can go through. One thing that we want to do here is I just want to get you used to working with it, and then you can dive in and start changing this. And that's the idea of the notebook, is you can start looking a little bit at the documentation, look at what your options are, changing it, and seeing the effect. So let's go ahead and split the data, construct the network, and compile it. And then we can go ahead and fit it. So this is going to feed in 100 at a time, 25 epochs, and we're going to see what happens if we start changing these. So let's go ahead, and it's going to run through 25 epochs of training. This may take a moment. Now, one of the things is, keep in mind here, you want to be able to the whole idea of this Colab notebook is you want to go ahead and be able to test this stuff. So try different numbers of epochs. I think when I talk a little bit about your exercise here, I mentioned adding a dropout layer. So the idea here is sometimes you can overtrain so that the parameters of your neural network, the estimated parameters, are really too focused on your trained data, so it doesn't work well with the test data. So you can see if you train it longer, are you overtraining? But then what if you trained it longer but added a dropout layer? A dropout layer basically just gets rid of some of the nodes randomly, so that in each epoch, so each pass through, and so it should prevent overtraining. So keep in mind all of these now. And that brings up another important thing to say. With this, a lot of it is trial and error. So if you go back to sort of, maybe you remember statistics and econometrics courses, they tend to say, okay, well, the model dictates this is how we should construct our statistical model. The theoretical model gives us insight into the statistical model. With this, there's no right answer or wrong answer. There's good guidelines, but a lot of it is trial and error. So definitely, what you want to do is try adding layers, try adding dropouts, try different activation functions. This is the function that makes the neuron fire. Try different numbers of epochs and see the effect. Good. So now we can go ahead and evaluate the model with our test data, and this gives us our loss of 0.93. That's not so important. We have it right here. But what we're going to go ahead and do is calculate our prediction error. So this trained the model, right? Now what we're going to do is we're going to feed in the test features, run it forward through the model, and get the test output. So that's going to give us our predictions. But then again, remember that this prediction is going to be normalized, so we have to unnormalize it here. So this is going to be our raw predictions. So we're running this test data forward through the model right now, and now we're sort of unnormalizing it, right? So we can see, if we want, we can visualize these are our predictions. So what we can do is calculate the average prediction error. So this is our predictions minus the actual, This is the sum of it. This is the absolute value, right? And then we're taking the sum of it and dividing it by the number of predictions. So we have an average prediction error of 0.19. So, and if we look at this, we might want to compare it to the standard deviation of the change in small business loans, right? So this is this is less, right? Which is good. Now, what we're going to do here is compare it to just a standard multiple regression model. So what we can do is go ahead and estimate a linear regression model, just using that same data into a linear regression model, and seeing does the neural network have a lower prediction error, average prediction error, than the regression model. It's a multiple regression. So we can go ahead and do that and calculate the prediction error, and 0.1933. So we beat it by a very small amount. And keep in mind, while I'm talking, I'll rerun this because this is estimating the parameters, right? You will get slightly different estimates every time you run this, and you'll get slightly different average prediction errors. But so we beat it by a tiny amount, probably an insignificant amount. But we slightly beat the linear regression model. And this is interesting because what you could say is, well, there is something called a fixed effects model where we're looking for, we're basically, what we've done away with here is identifying each bank. Right. So the fixed effects model will say, okay, well, this is this bank, and look at the change in this bank over time. So we could improve this multiple regression model by using panel data methods. However, that said, so we could bring this down. That said, we could also, what I've done here is just used a very simple neural network model. So you could also improve this neural network model. So the kind of amazing thing here is simply by constructing, basically the most simple neural network model I can do, and really without understanding any sort of the data, I can go ahead and at least match, beat slightly, just a regression model. So in other words, the neural network is performing, I'd say, fairly well. So let me see. I'm going to calculate the new. Oh, now it's worse. I've played around with this a little bit. I've added a couple. I've added another layer, and I've gotten this down to, I think the lowest I had was 0.16, 0.17. So you can get this down a bit. This one here, you can see that this one here won't change. So yeah, and when I actually ran it the first time, this was what I got from the neural network. So because I'm recording this, I'm getting slightly worse results, obviously. But while I talk, this will be the last. This will be the last time we calculate it. Good. Last thing I'll note here before talking about the exercise is there's a we can fit this. This will take some time, but we can look at sort of the history of evaluating the neural network, how it's doing over each training epoch and so forth. So you can go ahead and run this, and this will take a little bit longer to run. I won't run it here and kind of sit here, but go ahead and run this, and this is going to give you an idea of how the training is going over time. Lastly, let me go ahead and hide this. For your exercise, try to add another dense layer, and with that, whichever activation you would like, and re-estimate the model and see if your predictions improve. So if you add another layer, let's say 100 neurons, 50 neurons, whatever you'd like, does it improve? And also try, if you want, try a dropout layer to make sure that see if there's any effect if you were overfitting. And did I run this? Oh, it looks like it got worse again. Hopefully add another layer, and maybe it'll improve for you. Good. Excellent. Have a great day.